Have you ever wondered how linked data structures work in programming? Today, we explore a fundamental concept that makes this possible: self-referential classes. These classes are a cornerstone in object-oriented programming that allow us to create complex, interconnected structures. Imagine a class that contains a pointer or reference to an object of the same class type. This is a self-referential class. It's a bit like a box that contains a reference to another box of the same type. This concept is not only fascinating, but also incredibly useful, particularly in linked data structures such as linked lists, trees, and graphs. Let's take a linked list for instance. Each node in the list is an object that contains data and a pointer to the next node. This is implemented using a self-referential class, where the next pointer in the node class points to an object of the same node class. The head node starts the chain, with each subsequent node linked through this self-referential property. But it's not just linked lists. Self-referential classes find their use in more complex data structures too. Take trees and graphs for example. In a binary tree, each node has a reference to its left and right child nodes. Again, these references are self-referential, pointing to other objects of the same tree node class. The beauty of self-referential classes lies in their ability to create these dynamic, interconnected structures. They allow us to navigate from one node to another, traverse the entire structure, and even modify it by adding or removing nodes. So, the next time you're working with a linked list, a tree, or a graph, remember that it's the power of self-referential classes that makes it all possible. Now that we know what self-referential classes are, let's delve deeper into how they function. Self-referential classes are like a puzzle, where each piece is connected to another. They can be thought of as the building blocks of dynamic data structures in object-oriented programming. These classes contain members that are pointers or references to objects of the same class type. This allows us to create structures where objects are interconnected, much like a linked list, tree, or graph. To help you understand this better, let's dive into an example. We'll create a self-referential class representing a node in a singly linked list. In this class, which we'll call node, we have two members. The first is an integer data that holds the value of the node. The second is a pointer next that points to the next node in the list. Now let's create some nodes. We'll start by creating a head node with the value 1. Next, we'll create a second node with the value 2 and a third node with the value 3. At this point, we have 3 separate nodes, but they're not linked together yet. To link the nodes, we'll use the next pointer in each node. We'll point the next of the head node to the second node, and the next of the second node to the third node. Now we have a linked list where each node points to the next. But how do we traverse this linked list? We start from the head and keep following the next pointers until we reach a node where next is null, indicating the end of the list. As we traverse, we can access the data of each node to see its value. When we're done with the linked list, it's important to deallocate the memory we allocated for the nodes. We do this by deleting each node, starting from the head. So we see how we can create nodes, link them together, and traverse the linked list using self-referential classes. This powerful concept is the backbone of many dynamic data structures in object-oriented programming. But what about more complex data structures? Do self-referential classes have a role there? Absolutely! Self-referential classes are not only for linked lists, but also frequently used in more complex data structures like binary trees or graphs. In these structures, nodes have references or pointers to other nodes, creating a network of interconnected objects. Let's take a look at how this works. Imagine a binary tree. Each node in the tree contains a value and 2 pointers, one for the left child and one for the right child. This can be represented with a self-referential class, just like we did for the linked list. For instance, consider a class named TreeNode. This class has 3 members. An integer for the data, and 2 tree node pointers for the left and right children. The constructor initializes the data and sets the pointers to nullptr, indicating that the node doesn't have any children yet. In the main function, we can create nodes for a binary tree. We start by creating the root node, and then we add more nodes as its children. Each node is created using the new keyword, which dynamically allocates memory for the node. The pointers in each node are then set to point to its children. Now, traversing this tree would be a whole other story. There are several ways to do it, like in-order, pre-order, or post-order traversal. Each of these methods visits the nodes in a different order, depending on whether you visit the parent or the children first. And just like with the linked list, we need to deallocate the memory used by the nodes when we're done with them. This is usually done with a function that traverses the tree and deletes each node. From this, it's clear that self-referential classes provide a powerful tool for building dynamic data structures. By using pointers or references to objects of the same class, we can create complex interconnected structures that can be manipulated and traversed in various ways. And that, my friends, is the beauty of self-referential classes in complex data structures. So, what have we learnt today? In our exploration of self-referential classes, we've delved into the world of object-oriented programming, where these classes play a pivotal role. A self-referential class, as we've seen, is a class that contains a member which is a pointer or reference to an object of the same class type. This intriguing concept is the backbone of linked data structures such as linked lists, trees, and graphs. We've seen an example of a self-referential class in action, representing a node in a singly linked list. The class node had a member next, which was a pointer to the next node in the list. This allowed us to create nodes, link them together, and traverse the linked list. Our journey didn't stop at linked lists, however. We ventured further into the realm of complex data structures, exploring how self-referential classes are used in structures like binary trees and graphs. In our binary tree example, the tree node class had members left and right, each a pointer to another node in the tree. This allowed us to create a binary tree, with nodes connected to each other in a dynamic, intuitive way. In the broader picture, we've seen how self-referential classes empower us to construct dynamic structures, where objects are interconnected. They are not limited to linked lists or binary trees. They can be used in a multitude of scenarios, wherever we need to create a structure of objects interconnected in a specific way. But remember, with great power comes great responsibility. Dealing with self-referential classes requires careful memory management. While creating and linking objects is essential, so is deallocating memory when those objects are no longer needed. In summary, self-referential classes are a potent tool in object-oriented programming, enabling us to create complex dynamic data structures with ease. Their understanding and adept handling can open doors to a whole new level of programming prowess. And that concludes our journey through the fascinating world of self-referential classes. Remember, they are a powerful tool in your programming arsenal. Until next time, keep coding. Well, that was quite a journey, wasn't it? We've traversed through the realms of self-referential classes, from understanding their basic premise to seeing their application in complex data structures. If there's one thing to take away, it's that these classes are a powerful tool in your programming arsenal, capable of building dynamic, interconnected structures. The examples we've discussed today, like linked lists and binary trees, are just the tip of the iceberg. There's a whole world of data structures out there waiting for you to explore. The beauty of programming is that it's a field ripe for innovation and creativity. So why not take this knowledge and see where it leads you? Perhaps you could experiment with creating your own self-referential classes, or apply these concepts to a project you're currently working on. You might be surprised at how these classes can simplify your code and make your data structures more efficient. But remember, like any tool, self-referential classes are not a one-size-fits-all solution. They have their strengths and weaknesses, and it's important to understand when and where to use them. They are best suited for situations where you need to represent relationships between objects in a way that's easy to navigate and modify. And of course, we're here to help you on this journey. If you have any questions about self-referential classes, or if there's something you're not quite sure about, don't hesitate to drop us a comment. We're always eager to hear from you and help you navigate the world of programming. Remember, programming isn't just about learning concepts. It's about applying them, experimenting with them, and most importantly, enjoying the process. So keep exploring, keep coding, and keep pushing the boundaries of what's possible. Thanks for joining us in this exploration of self-referential classes. Don't forget to subscribe for more interesting content. Happy coding!